Space, the final frontier. But how do we get there? Why, it's through, well, no, rockets, of course. Yeah. But how do they work? What fuels them? Magic? Nukes? The government? Well, actually, the answer is more simple than that. It's actually rockets. So you have the payload up top, but it only makes up for a very, very little of the total mass. So what fuels it? Well, first you have the fuel, to combust it. But in space, you have no oxygen. Therefore, you need your own oxidizer in some cases. So the rocket brings its own supply, usually in the form of liquid oxygen. Finally, in the combustion chamber right here, the fuel and the oxidizer mix combusts and is shot out the nozzle. And this is how the rocket moves. So in accordance to Newton's third law, for every action there's an equal and opposite reaction. As the exhaust pushes down, the rocket pushes back up, equal force. So let's take an example. Let's look at the Saturn V. Everybody knows what the Saturn V is. So it was basically the rocket that got people out into the moon, Apollo 11. It was a 3-stage liquid-fueled vehicle, and as of 2018, it was still the tallest, heaviest, most powerful rocket before being displaced by the Falcon Heavy, that you just saw in the video. And it had a payload of 140,000 kilograms, which is still by far the heaviest payload ever put into space so far, and a mass of 2.97 million kilograms, which is just absurd. And it had a height of 110.6 meters. So, how long does it take to accelerate the Saturn V to 11,000 meters per second? Well, first of all, we need to find the resultant force, which is basically the thrust minus the weight. And from there, we can find the acceleration, and then from there, we can find the time needed to accelerate to 11,000 meters per second. So first of all, like I said, production value is not going to be good, but 2.97 God damn it, million kilograms of mass. However, you're fighting against the force of gravity, which is 9.82 meters per second squared, which gives a result of 65,400 newtons of weight. A liftoff. You just gotta do the math, right? So at liftoff, the Saturn V had 5 F1 engines in the first stage, which was enough to produce 33,361,662 newtons of thrust. Now, how do I know this? Google. Thank you, Google. To get the resultant force, you need to have thrust minus the weight, which is the thrust, which we found using the power of Google, is 33,361,662 newtons minus the initial 29,965,500 newtons to give a resultant force of 4,196,262 newtons. Boom. Look at that. That's math. Now, to find the acceleration, we have to use Newton's second law. So F equals ma, nice and basic. We have the resultant force, so we can rewrite that as the resultant force over the mass initial to get the acceleration. So if we take 4,196,262 newtons over the initial 2.97 million kilograms, we get an acceleration of 1.41 meters per second squared. Now, to get to the escape velocity, we need the velocity distance equation to find the height difference, and then from there we can use the position time to find out how long it would take at a constant acceleration of 1.4 meters per second squared to get almost 3 kilograms of weight off the ground. So v final squared minus v initial squared equals 2a delta x. Well, delta x, delta y, you know what I mean. So we find that the rocket starts at rest, so v initial squared is 0. V final squared is 11,000 meters per second, which is squared, equals 2a delta x. Delta x turns out to be 4,200. Oh, no, wait, hold on. 81 meters. Yeah. Or 42,907 kilometers. And then from there, we have the delta y. So we can use the position time graph to find the time. So y final equals y initial plus v initial time plus 1/2 at squared. Now, we start at ground level, so y initial is 0. We know y final, which is, 81 meters. 42,907,801 meters. Yep. Equals to v initial, which is also 0 because it starts at rest, 1/2 the force of gravity, 9.8 meters per second squared, t squared. And so you do the math, and we find that the time is 2,956 seconds, or 49 minutes. Wait a minute, but that's wrong. What's wrong? What happened? In reality, the first stage burned for 2 minutes and 41 seconds, all the way up to 68 kilometers, and reached speeds of 2,756 meters per second, burning 2.1 million kilograms of propellant, which is around 70.7% of the total mass. The reason why we got these numbers for 42,907 kilometers and a time of 49 minutes is because we forgot to take into account the 3 stages of the Saturn V. In this case, we're assuming that the mass stays the same, which it doesn't, because the fuel is being used. Once the stages are used, they're dropped off so that the rocket can move on to the second stage or the third stage, have less weight to carry, and have more thrust. So that's why, the numbers are wrong, but, in this case, to accelerate to 11,000 meters per second at a constant mass of 2.97 million kilograms and a constant acceleration of 1.41 meters per second squared, it takes 49 minutes. So, yeah. In reality, the second stage burned for 6 minutes and lifted the craft to 175 kilometers and reached speeds of 6,995 meters per second. And the third and final stage lasted for 2.5 minutes, put the rocket up to 191.1 kilometers and reached the speed of 7,793 meters per second for a total burn of 11 minutes and 40 seconds, which is about 1/4 of the calculated time. But hey, this is, rocket science, and I'm just physics 110, so yeah, just doing my best here. The end.